my name is Tessa Fitzgerald. I'm a PhD student working with Dr. Ashok Goel and Dr. Andrea Tomas. I'll be talking to you about our work on human-guided object mapping for task transfer. We're motivated by the goal of having the robot learn a task from demonstration and then be able to transfer that task to a new environment which may contain different objects or a different configuration of objects and so on. In order for the robot to successfully transfer what it's learned to this new situation, it needs a mapping of which objects in the source environment map to which objects in the target environment. For example, in this case, the red bowl maps to the blue one. But this problem is further complicated by how object mapping in real-world tasks is a contextual problem. Here's an example. Let's say that the robot has learned a series of tasks in this environment here at the left, and then is asked to repeat those tasks in a later environment here containing a set of Legos. If the robot is repeating a stacking task, the mapping might look something like this, where objects are mapped to each other based on their size, so that larger objects are stacked first, to smaller ones, and so on. But if we instead ask the robot to sort objects by color, we would expect a mapping that looks more like this. Previous work that's addressed these sorts of problems has mostly focused on those where we know which feature to use in order to map objects to each other, such as visuospatial similarity, or shape, or other features such as that. Or rely on having the robot continue to get additional experience in the target environment in order to infer the role of objects in that task. We take a different approach by continuing to leverage interaction with a human teacher. Assuming that the teacher has already provided a demonstration of a task, we presume that the teacher also knows how the robot should adapt that task to the new environment. So to outline our approach, we enable mapping by demonstration by first having the robot receive a demonstration of a task, and then put it into a new environment which contains different objects. Once the robot is able to observe these different objects, we then provide assistance to it in the form of indicating which object it should use next for an ordered task. Using this assistance, it is able to define a correspondence between that object and the one that it would have used in the original task. Using that assistance, the robot then predicts the rest of the mapping, and then can either ask for additional assistance or, if it's confident in its prediction, use that mapping to transfer and then execute the task in the new environment. Our work primarily focuses on these two steps of how the robot can receive assistance and then use this assistance to predict the mapping for the rest of the task. In doing so, we leverage assistance from the human teacher in order to perform object mapping, without requiring that the robot gain additional experience or exploration in the target domain. This also allows us to avoid making assumptions about which particular object feature the robot should pay attention to during object mapping. So to get more into the algorithm for this, we first consider that each match between an object in the source environment and an object in the target environment is one object correspondence. This is what's indicated by a single assistance provided by the teacher. An object mapping then consists of one object correspondence for each object trying to be mapped. What this leaves us with is a full set of all the possible mappings that the robot could consider, and this is what we call the mapping hypothesis space. Now, it would be easy if we could just say, let's find the mapping in the mapping hypothesis space that maximizes total similarity between corresponding objects. But of course, this relies on us having a measure of similarity, which again is difficult here because it's contextual. It's dependent on the task being performed. So not only should the robot consider the whole mapping hypothesis space, but it also has to consider the set of features to use in order to evaluate those mapping hypotheses. So we consider both of these at the same time. In order to address the mapping hypothesis space, every time that the robot gets an assist from the human teacher, it's using that to prune its mapping hypothesis space to only those that support the assistance that it just received. At the same time, it's then using a set of features to evaluate all those mapping hypotheses. Here in our work, we considered 7 different features based on perceptual features such as hue or dimensions. We also considered several knowledge-based features such as spatial relationships between objects or affordances or properties. There's more details about this in the paper. But one major takeaway is that even though we included these 7 features, we don't claim that this is a complete set. but rather our approach is flexible for additions of new features. Using these features, we define a similarity function based on the minimum and maximum values of each of these features. So then after receiving assistance, we prune the mapping hypothesis space and evaluate every combination of mapping hypotheses and features in order to predict the highest ranking or most similar object mapping. And this is the mapping that gets returned at that point in time. Now at this point, the robot can either continue to ask for more assistance or use this predicted mapping to transfer the task right then and there. So to evaluate this approach, we first performed an extensive simulated evaluation, which was aiming to answer the question, can we even use this type of assistance to infer the correct mapping? We performed 780 mapping evaluations in simulation using ground truth assistance, so basically getting the assists from an oracle rather than from a human user. We then performed an interactive evaluation where we performed a 10-user study in which we had users actually provide assistance to the robot. And the intention of this is to determine how does interaction with a real human user affect our algorithm performance. And then finally, we performed a post-evaluation analysis of confidence in order to determine how much assistance the robot really needs to perform mapping and whether the robot could moderate its own interaction. So to start with our simulated evaluation, we performed evaluation in 3 sets of problems defined by the number of objects to be mapped. So here we have a 5-by-5 problem, 5 objects being mapped to 5 other objects in the target environment. And we compared our approach, MBD, mapping by demonstration, to 2 baselines. The first one being if you were to just randomly select a mapping from the hypothesis space, which of course does very poorly. The other baseline being if we use assistance to just prune the hypothesis space rather than infer the correct features. And what we see is that when the number of hints that we provide to the robot, or number of assists that we provide is limited, we see a major difference between the baseline performance and mapping by demonstration. So in cases where we are data limited, it's especially important that we use interaction to the fullest extent as we do in the mapping by demonstration algorithm. We see that this is even more important as the problem complexity increases. So for 6 object and 7 object mapping problems, the problem space grows exponentially. And so it becomes even more important to use assistance from the human teacher to infer not just the mapping hypotheses, but which feature to use to evaluate those hypotheses. Next, in our user study, we wanted to see how does interaction with an actual user feed into this algorithm. So we had 10 participants provide demonstrations of pick-and-place tasks, and then provide assistance where they would either point to the next object to be used or hand that object to the robot. We used 3 different tasks in this evaluation, each differing based off of their object features, the feature to be used to find the correct mapping, and the number of objects used. So here on the right we have a lunch packing task. This one, even though it had the most realistic objects, it was the simplest one to approach because there were only 4 objects. And what we found is that in this case we actually didn't need any assistance to correctly find the correct mapping. And this problem here at the left, the stacking task, this contains 5 objects, so it was a little bit more difficult. And what we found is that our algorithm needed fewer than 2 assists to be able to predict the correct mapping. And then for the third task in the middle, the sorting task, this one was the most complex with 6 objects to be mapped. And the robot needed 3 or fewer assists in 9 out of 10 cases to find the correct mapping. So something interesting to note is that, first of all, some mapping problems can be addressed without any assistance, as we saw with the lunch packing task. But for other tasks, such as, especially for the sorting tasks that are more complex, a little bit of assistance actually drastically improves performance. We found something else that was very interesting, which is, at a certain point, performance may actually decrease with additional assistance. So we looked into this further and wanted to see what we could do about this. First of all, this decrease in performance may be due to a number of factors, but particularly if the assistance that the robot receives is incorrect. This could be due to a number of factors such as sensor noise, interpreting where the user pointed incorrectly, the user changing their mind about which object they wanted to hand the robot, and so forth. So what we found is that overall, while assistance was useful at a certain point, too much assistance introduced more opportunity for error. So we look to address this by introducing a measure of confidence. We consider confidence to be based off of the decision margin between the top two object mappings being considered. And what we find here is that, of course, as you increase the confidence threshold, before the robot stops asking for assistance, it'll ask for more assistance. So the number of assists that the robot requests is tied directly to that confidence threshold. What we found is that we were actually able to define a confidence threshold that maximized performance across all three tasks. What this means is that we were able to find a certain point at which the robot was confident enough in its mapping, thus maximizing its correctness, but another effect of this is that it's also maximizing its autonomy. So by reducing the number of assists that it asks the teacher for, it's able to complete the rest of the task autonomously without additional help. What we found is that with this selected confidence threshold, this resulted in correct mappings in 93% of cases with our user study. In our evaluation, we were able to use the same confidence threshold across all three tasks, but more evaluation will be needed to see how well this generalizes or if it's based on a particular feature of the task. So to wrap up, the contributions of our work is that we were able to find that by inferring the relevant object features, the robot was able to more quickly use interaction from the teacher to identify the correct object mapping, and that this is especially important as the problem size increases. We also find that by situating this problem in additional interaction with the human teacher, the robot can leverage this interaction so that it only needs between 1 and 3 assists to handle the rest of the task autonomously. Additionally, we found that using this assistance provides the robot with useful help in order to transfer a problem, but too much also introduces some room for error. And thus the robot needs to moderate this interaction in order to maximize its performance. And finally, we found that using a confidence threshold allowed the robot to do this and resulted in correct mappings in 93% of cases in our user study. With that, I'd like to thank our funding sponsors and invite your questions. Thank you.
Great, thank you for the talk. Do we have questions from the audience? We do have a couple of minutes. Over here, please. There's 2 questions, and also one further forward.
Really cool work. So in this work, you're using these surface features to compare, to find the mappings between these different situations.
Right.
This seems to be in contrast between with work in analogical reasoning, for example, which would look, instead of looking just at the surface features and looking at the relationships, the structural relationships between the different objects. Have you considered maybe augmenting your approach with that sort of relational, structure-based approach? Yeah.
Right. So structure-based mapping is definitely something that we considered here. I wouldn't say that this is actually in opposition to that, but rather that we're not assuming a single feature for that mapping. So the structure-based approaches tend to assume that those visuospatial features or contextual features are the only feature that should be used for mapping. And here we do include relative position as one of our features. And so I consider that to be I consider our approach to be taking on those features and then adding several more as well.
Hi, thank you so much. So I wanted to ask, actually, ascertain if there's a limitation of mapping, that it has to be a one-on-one mapping, or it could come to a one-to-many or many-to-one mapping.
Right. So in this work, we only addressed one-to-one mapping. That was so that we could focus on directly relating the role of interaction to performance without bringing in other variables, such as whether it's a one-to-many or a many-to-one kind of mapping. I do believe that this approach could be transferred to those cases. It just fell outside the scope of our evaluation.
And also, is it important to keep the number of objects in the source and the target equal, or it could vary?
In our work for this implementation of our approach, this was only for one-to-one mapping, so keeping the number of source and target objects the same. But this approach could be extended to 5 to 6 mappings, 5 to 7, and so on. But just for the sake of leaving out one variable in our evaluation. To keep that more simple, we didn't address this in our current work.
Please join me thanking our speaker again.